Hi everyone, I'm Zhichen from School of Artificial Intelligence and Automation, Huazhong University of Science and Technology. Today we are talking about our paper, Cascade Network, with guided rules and hybrid attention for finding good correspondences. Two-way geometry estimation, which means establishing reliable correspondences and estimating relative pose between an image pair, is a fundamental component of many tasks in computer vision. Recently, some methods placed the task of finding correct correspondences as a binary classification problem and solve it by neural network. Specifically, these methods first obtain a putative correspondence set of an image pair by extracting local features and matching. Then, the network takes the putative set as input and divides them into inliers and outliers, and estimates relative pose. Although many recent methods have achieved excellent performance, we believe that there are still two problems worth solving when using deep learning network for finding correct correspondences. First, due to various reasons, such as the wide baseline, scale change, and so on, the number of outliers in the putative correspondence set is much larger than inliers, which usually results in a class imbalance problem of binary classification. As shown in Figure 1, we trained the same network with two commonly used loss functions, including cross-entropy loss and instance balance cross-entropy loss on a class imbalance dataset, and present the training curves of precision and recall. These two loss functions can elevate the class imbalance problem to some extent. In some tasks, however, they lack a direct connection with precision and recall, making the network unable to dynamically adjust the balance of precision and recall. Figure 1 has demonstrated that even though the precision and recall have been severely unbalanced during training, the loss function cannot adjust the training direction to narrow the gap between precision and recall. In fact, too low either the precision and the recall will lead to inaccurate relative pose estimation. Thus, balanced precision and recall are very important. Second, besides loss function, another challenge is how to better encode global context. Unlike 3D point cloud, not each correspondence contributes to the global context. In construct, outliers are noises to the global context. This issue is previously explored by introducing spatial attention in the network. These methods learn a weight for each correspondence and learn global context so that the network can allow for outliers to be ignored. The key to this approach is that the weight of outliers must be lower than inliers when encoding global context. However, learning appropriate weight for each correspondence in advance is a chicken and egg problem. In the shallow layers of the network, it is hard to learn appropriate weight because the features in these layers are less recognizable. Next, we will introduce the way we propose to solve these two problems. First, we introduce the proposed guided rules. Let's look again at the recorded training curve when use CE loss as loss function. Both two types of CE loss functions lead to an unbalanced distribution of precision and recall, which results in a low FN error. Let's look at the curve of the recorded loss function. Fortunately, loss has been falling during training. However, there is no guarantee that a drop in the loss will result in an increase of FM error. Therefore, the network may not be trained towards the direction of optimizing FM error. Based on this observation, we propose that is whether a relationship between cross-entropy loss and FM error can be established so that the decrease of loss will lead to increase of FM error. Thus, optimizing loss function is optimized FM error. This functional relationship can be expressed in the form of differential as follows, which is d loss times dfn is smaller than 0. Specifically, the form of our loss is the same as the instance balance cross-entropy loss as equation 1 in this slide. Different from instance balance cross-entropy loss, the lambda and mu are changed during training in guided loss, while lambda and mu are unchanged in the instance balance cross-entropy loss. We rewrite equation 1 as equation 2 in this slide. Well, x and y is the number of Fn and Fp samples. Meanwhile, Ntp equals n poles minus x. Ntn equals nnag minus y. Then the precision and the recall can be expressed by x and y. Since FM error is computed by precision and recall, thus FM error can also be expressed by x and y. We denote the functional relationship between Fn, x, and y as f. We computed the derivative forms of loss function and the FM error by x and y as equation 1 in this slide. Then we draw a conclusion, that is, equation 2 is a sufficient condition of equation 3, which is dl times dfn is smaller than 0. Thus, we design an algorithm called the guided loss. The main idea of guided loss is to keep equation 2 holds during training so that a drop in loss function will lead to an increase of FM error. Thus, the network are trained in the direction of maximizing FM error. The algorithm of guided loss is presented in this slide. The input of guided loss is the classification result after forward propagation. The output of guided loss is the weights of precision of positive and negative samples in loss function, which is lambda and mu. For each image pair of a batch, we count the number of n poles and n nag, and also count the number of NTP, NTN, NFP, and NFN. Then we compute the average loss of TP, TN, FP, and FN samples. Finally, we can compute lambda and mu. Specifically, when a batch of training data set is sent to the network, the first step is forward propagation. After the forward propagation, we can use algorithm 1 to get lambda and mu for making equation 12 in the paper hold. Then we substitute the lambda and mu into the loss function and perform back propagation. We also present the proof of guided loss as follows. We do not introduce the process of proof in detail here. Then we introduce the hybrid attention block. It is the basic efficient extraction block of our network. As shown in this figure, the input of HAB is the feature map. Specifically, BACN is to normalize each correspondence so that the features of correct and incorrect correspondences are distinguishable. BN is adopted to accelerate the network convergence, and the ReLU function is utilized as an active function. Finally, the CA operation learns a statistical information on the channel to boost the performance of the network. We first briefly introduce how our BACN learn distinguishing for features for inliers and outliers. In fact, the inliers are under the constraint of an E matrix, while outliers are not. In BACN, a global context is utilized to replace the constraints of E matrix to normalize each correspondence. We use statistical information, which means the mean and the variance of all the features, as the global context. Since the global context is expected to fit the distribution of inliers, we use a weighted mean and variance as global context so that the outliers can be ignored by the weight vector. Then, we use the context normalization operation to encode a feature for each correspondence. The key to BACN is how to better learn the weight vector for computing weighted mean and variance. In the shallow network, it is hard to learn appropriate weight vector because the features in these layers are less recognizable. Since Rowley rate, which is generated during feature matching, is proved useful for determining the confidence of each correspondence being an inlier, we expect to use it to make up the weight vector learning in the shallow network. However, the distribution of Rowley rate is quite different on different datasets, while independence and identical distribution of features is very important assumption in neural network. To make better use of Rowley rate, we first use the Bayes model to convert it into a probability value. After that, it will be utilized to participate in the calculation of weight vector. The architecture of weight learning is inspired by Bayes model. The prior probability is similar to the prior probability of Bayes model. Meanwhile, as shown in the figure, the input of BACN is followed with two conclusion operations to learn a temporary weight vector, which is similar to the likelihood probability of Bayes model. The prior probability and the likelihood probability are fused through a feature concatenation operation to generate a feature which encodes the information of a posterior probability. After that, the posterior feature is followed by two convolution and softmax operations to produce weight vector. By incorporating prior information, our network is easier to obtain better classification results. Meanwhile, the statistics on the channel have been shown great impact on the network. In order to enhance the channel awareness of the network, we introduced channel-wise attention to HA block. We learned a channel weight vector for each correspondence instead of weight vector that is shared by all the correspondences. To capture complex channel contexts, when learning the weight vector, group convolution is used to reduce network complications. Since the proposed guided rules can flexibly control the based on precision recall by using different ephemeral schedules, we can naturally build a cascade network by guided rules to progressively refine the performance. Specifically, as shown in this figure, we first use 12 layers of hybrid attention blocks as feature extraction model to extract the feature for each correspondence. Then a coarse result can be obtained through these features by Fn1 measure guided loss. Then two refinement models are followed to perform local optimization to refine the cost result. Each refinement model is made up of an 3-layer HA block, different from the feature extraction block. The global context in refinement model is extracted from the cost result of the previous model instead of all of the correspondences. Besides, in order to gradually optimize the cost result, the loss function will also progressively based to the precision. The cost result 2 is obtained by Fn2 measure guided loss, and the final result is obtained by Fn3 measure guided loss. During training, the N1 is greater than N2, and the N2 is greater than N3. So that the network gradually obtains the result with higher precision. Finally, the E matrix is computed by performing weighted 8-point or ransack algorithm on final result, and it is supervised by a L2 loop. Next, we present the overall performance of our network. We compare our network with other state-of-the-art methods, including CNNet, PointNet, ACNNet, NMNet, N3Net, and OANet on both two datasets. These experiments demonstrate that the proposed network behaves favorably to the state-of-the-art approach. We then perform ablation study. We first analyze the function of each proposed model separately. Then we concretely analyze the proposed guided loss. Finally, we also visualize the results compared with ransack CNNet. That's all. Thanks.